Today we'll talk a little bit about significant figures. Significant figures, the title is kind of strange and doesn't make much sense all by itself. The word significant here is not my favorite choice of words for what we're actually doing with this. And figures, it's not my favorite either. So I'm going to suggest a couple of replacement words that make more sense, hopefully, for what we're going to be doing in the class. Oftentimes you'll say significant digits instead of significant figures. So I like the word digit better, and that meaning like a number. A number is a digit. So we're talking about numbers. Significant figures are not talking about people and how large they are and how big their figure is. Like my figure is more significant than many of yours. But that's not the point. We're talking about digits, numbers. Now, significant here can be replaced with a very simple word. Since in science, usually we're dealing with things that have been measured, we're talking actually about measured digits. Significant figures, so it's measured digits, numbers that were measured with the device. And this is important because there's a lot of ways you can write a number. And if you write it incorrectly, it might not show exactly how you measured it. And scientists like to we use significant figures basically to show not only the number that we measured, but how we measured that number. And that'll make more sense hopefully in just a minute. We'll start with this. Since this is toward the beginning of the school year, you'll need to know how to use one of these if you haven't already figured out how to do so. This is a meter stick. Notice on the meter stick we have these things called cm. That stands for centimeter. So there's 1 through 100 centimeters on that meter stick. The 1 meter being, of course, 100 centimeters. There are also these little marks on here. By the way, a centimeter is 100th of a meter. There are 100 of them in a meter, so it's 100th of a meter. And the little marks on here, there are 1,000 of them if you go all the way across. So they're 1,000th of a meter. We call them millimeters. And if you read the module, you know how the prefixes work, centi versus milli, and how those all play out. So we have centimeters and millimeters. If we wanted to measure something like this is just a piece of plastic from the back of a laptop screen. This is from the backlight. Let's take this and measure it. We'll make a couple measurements. And remember in your math class that we talked about, or not we, but you talked about, length times width equals surface area. Thank you, everyone. So surface area. We'll take this guy here, and let's get a length measurement on this. And we'll write it on the board here in just a second. It looks like, let me push that edge a little better. If I'm not mistaken, that's almost exactly 37 centimeters. And notice, it really depends on how you look at it. If you change the angle on that, it could look like a different number, like 37.5. You want to look straight on. That's called parallax when you're not looking directly on something. So, 37. No parallax error, 37 centimeters. Now, here's where it comes in. I said you could write things multiple ways. I could write 37 centimeters like that. Right? Well, we don't want to write it like that. That's incorrect. Because we have the ability to measure millimeters. It's right on the millimeter mark. So it's 37 and 0 millimeters. 0.0. A millimeter is a tenth of a centimeter. We're going to show that we had 0 of them. So we measured that 0. It's a significant figure, or a measured digit. So we write it, because we had the marks on the stick. If we didn't have those marks, we just had centimeters, then 37 would be our answer. If we just had every 10 centimeters, then it would be closest probably to 40 centimeters. So it would be about 40 centimeters, and in that case you'd write it like that. Now, we have to write that 0 to show that that 4 isn't 4, but that 0 really didn't measure anything if we only had every 10 centimeters marked. There were only 4 things that we looked at, that we moved past, and we only have 1 digit that we measured, and that's this 4 right here. So this 0 is not significant. If you have to write a number that ends in a 0 like this, and you measure that 0, you write a decimal right there. And scientists know to do that. So if in your book you see a number like this with a decimal, that means there are 2 measured digits, or 2 significant figures. If you don't see a decimal there, that 0, again, it's just there as a placeholder to show that we didn't have any 10s, that we didn't have any 1s, we just had 10s. So that placeholder just tells us that 4 is not 4, it's 40. And it's not a measured value, unless we write it the correct way. Alright, so back to the idea of area. Now length times width equals area. Don't ask me what that was on the end of there. But sometimes little things creep onto the chalkboard that shouldn't be there, and when they do, that's chalkboard error. It's not my fault, it just happens sometimes. So don't hold it against me. Now, one more measurement. Let's get the width measurement on this. You'll have to help me out here, class, because I might not be able to see it. 23.4, looks like. Thank you, class. 23.4. So, 23.4. Seems easy enough to know that we need to write that 4 there, because we measured 4 little marks. Just don't forget to write those zeros when those come up. Alright, so this is our length, this is our width. Now we can calculate area. Now before we calculate area, there's a problem. There's 2 sets of rules that you need to follow. And I'll just tell you these rules flat out, even again in the module. They're written out on paper, so maybe if you're one of those you learn from reading, then go do that. If not, listen carefully here. When you're multiplying numbers and when significant figures come in, you need to keep the number of digits that you had in your least significant number coming in to the problem. So right now we're going to multiply these 2. Both of these have 3 significant figures, or measured digits. So we're going to be able to keep 3 digits in our answer. But say we didn't measure 37 here. It was 37.0. Say it was just 37. We really didn't have the millimeter marks there. Then we have 2 significant figures and 3 here. When we multiply them, we can only keep 2, because one of the numbers that we put into the multiplication problem had only 2 digits, and that was the smallest number of significant figures out of all of the measurements we made. That's how many we can keep. So you're limited to your least significant measurement. If I make one measurement that has only 1 digit, that's all I can keep. Even if I made 20 numbers that had 20 digits. If I have one that has 1, that's all I can keep. So you can't be any more precise than your least precise measurement. Now, we take them here, 37.0 centimeters times 23.4 centimeters equals something. We'll use our handy dandy calculators here. I don't know if you can see that or not. Got a lot of glare here. 865.8. Now, you are smarter than a calculator. The calculator just lied to you. What did I say? We could keep 3 digits? The calculator gave us 4. The calculator doesn't know the rules. The calculator thinks we might be a math student. And math students don't know the rules either. We're not. We're physics students. We know the rules. We can only keep 3. We're going to keep the 3 largest value digits. 8, 6, and 5. Well, 5 here is followed by 0.8. It's going to round up. So, 8, 6, 6 centimeters squared is our value, with significant figures included in there. And that shows that our measurement, when we made them before we calculated, had 3 significant figures in every one of them at least. This one, in order to get that value, as a scientist, we would have to have at least 4 digits in every one of the numbers that went into the problem. We didn't have that.